Welcome to 2.5. What a grandiose name this has. The fundamental theorem of algebra. The single most important base of algebra comes from this. And then when we see the linearization factor theorem, we learn right away the fundamental theorem of algebra that leads to that is probably not as important for us to really know as the linear factorization theorem, although once again it is the fundamental. It got us to the linear factorization theorem. Let's take a look. If we have a polynomial, and we all know what polynomials are, of degree n, where n is greater than 0, in other words, our polynomial isn't just f of x equals 7. There's an x term, at least an x term in it. Then f has at least one 0 in the complex number system. Of course, here's a second degree polynomial that doesn't have this parabola, doesn't have any real zeros, but it's saying this would have at least one 0 in the complex number system. But then the linear factorization theorem says if f of x is a polynomial of degree n, where n is greater than 0, then f has precisely n linear factors where these c's are complex numbers, such as 3 minus 2i. Okay, so they could be complex numbers in here. So what that's telling us truthfully is that there are not just at least one, there are exactly n zeros, assuming that we can count, for instance, this graph right here, y equals x squared, has two zeros if we count this as a double 0. It's a 0 twice. In other words, this could be f of x equals x minus 0 squared. So we would say that 0 is a double 0. More to come about that topic. Okay, so this linear factorization theorem kind of trumps the fundamental theorem of algebra, takes it to the next step. If I have a third degree polynomial, there are 3 zeros, provided I can count those as double or triple zeros, not just at least one. If it's a 7th degree polynomial, we have 7 zeros or 7 factors, assuming we can go into complex numbers and assuming that we may count some as doubles, triples, etc. Okay, this is a biggie, and sometimes math is hard to read, but this says it all. Complex zeros occur in conjugate pairs. In other words, if 3 plus 4i, if we know it's a 0, so is 3 minus 4i. And some of that can be understood because if you think about quadratic formula for a moment, opposite of b plus or minus root b squared minus 4ac all over 2a, here's where we get an imaginary number when we get b squared minus 4ac is negative, and look where it's at, right behind a plus or minus. So that's where we get this from. Complex zeros occur in conjugate pairs. That's a biggie for us. And factors of a polynomial, every polynomial of degree n is greater than 0 with real coefficients can be written as the product of linear and quadratic factors with real coefficients. Now, we'd have linears and then we'd have quadratics in there, but the quadratics, if we went to quadratic formula on some of those might, if we tried to factor those, we might need to add in our complex numbers into that, where the quadratic factors have no real zeros. Okay, let's take a look. Find all the zeros of the function and write the polynomial as a product of linear factors. Okay, so my first hope would be I could factor this. Are there factors of -2 that add up to +6? No. So I'm going to go to quadratic formula. X equals the opposite of b plus or minus square root of b squared 36 minus 4 times 1 times -2. I'm just going to write it out that way. 4 times 1 times -2 all over 2 times a all on 2 is -6 plus or minus root 36. I can't tell you how many times really strong students miss this. I get negative times negative positive, that is plus 4 on 2, -6 plus or minus root 40 on 2, but root 40 is 4 times 10, 4 times 10, square root of 4 is 2 root 10 on 2. And here's where mistakes are commonly made on this. I can't reduce the 6 and the 2. I can't reduce the 2 and the 2, but I can reduce the top and the bottom, reduce the entire top by 2, negative 3 plus or minus just one of these root 10s on 1. So there are my zeros right here, negative 3 plus or minus root 10. Find all the zeros and write the polynomial as the product of linear factors. So this would be equal to x minus this thing. So x minus negative 3 would be plus 3 and minus root 10 times x minus the negative root 3 would be plus 3 and minus minus would be plus root 10. Okay. All right, let's take a look at 28. This is not quadratic because it's fourth degree, it's quartic. However, it is quadratic in nature. It is quadratic on x squared. So there's a possibility maybe I can factor this as x squared, because first times first, x squared times x squared equals x to the fourth. I don't know if I can do that all the time. Are there factors of 100 that add up to 29? 4 and 25. So plus 4 plus 25 gets the job done here. And if I'm looking for the zeros, I'm going to set that equal to 0. And so either x squared plus 4 equals 0 or x squared plus 25 equals 0. That is x squared equals negative 4 or negative 25. So that would be x equals plus or minus square root of negative 4 or square root of negative 25. So x equals plus or minus 2i, 5i, plus or minus 5i, which would give me factors. So I have f of x equals, see if I can squeeze this one in here, x minus 2i, I'm not going to be able to, times x plus 2i, my apologies, times x minus 5i, times x plus 5i. Okay, now 32, cubic. I'm going to get 3 zeros in the complex number system, and maybe all 3 of them are real, but I need to get this thing broken down somehow, and we're supposed to be doing this one by hand. Well, from previous section, we know that the factors must be, if there is a rational zero, and I pretty much know there's a zero because a real zero, because to the thirds look like this. They might be loopier, but they look like that. But if there's a rational zero, it would be a factor of 29 on a factor of 1. So like either 29 on 1, or the only other factor is 1 on 1, plus or minus. Well, maybe 29 or negative 29 works, but I'd certainly work with 1. But I quickly see if I put in a positive, I get positive plus positive plus positive plus positive. That can't be 0. So I'm going to hope negative 1 synthetically divides this thing. We can almost do that one in our head, perhaps. Negative 1, this would be negative 1, plus 11, 10, plus negative 39, negative 29, plus 20. Yeah, I think that's going to work. So I'm going to run negative 1, excuse me, synthetically through 1, 11, 39, 29. I expect to get a 0 here. So that's 1 and negative 1 and 10 and negative 10 and 29 and negative 29 and 0. So right now I would have this factored into x minus negative 1, x plus 1 is a factor, and the remaining factor is x squared plus 10x plus 29. I'm interested in where that would be 0, so I'm obviously negative 1 is a 0. So now I'm looking to factor this, but I can't factor. There are not factors of 29 that add up to 10. So x equals opposite of b plus or minus square root of b squared, 100, minus 4 times a1 times c, 29, all over 2a. And I'm going to get into imagination land here in a hurry. Negative 10 plus or minus. This is 100 minus, well, 30 times 4 is 120, 4 less than that, 126. Or 120, I'm sorry. 30 times 4 is 120, 116. 116. All on 2, I get negative 10 plus or minus root negative 16, 100 minus 116, all on 2, or negative 10 plus or minus 4i, all on 2. So my zeros are, I needed to give myself more room for this. My zeros are negative 1 from above, and then reduced by 2 here, top and bottom, negative 5 plus or minus 2i. There's my zeros. And now for my linear factors, apologies for taking up too much room here. I might redo this, but I probably won't. This in factored form could be x minus negative 1, x plus 1, times x minus, the first one I'm going to put in there is negative 5 plus 2i. When I subtract that, I get plus 5 minus 2i. And the next one I put in there is going to be negative 5 minus 2i. When I subtract that, I get plus 5 plus 2i. So this is times, again, apologies, x plus 5 plus 2i. So those are my linear factors. All right, I'll do better here with spacing, although we got a lot going on with this one. Once again, factoring this, I'm not sure of a conventional method to factor this, so I have to try to find something that divides this. The good news is it's factors of 9 on 1, so my only possibilities are plus or minus 1, plus or minus 3, plus or minus 9. But if everything's positive, I can eliminate all those pluses. So it's only negative 1, negative 3, or negative 9. If I put in negative 1, let's see, if I put in negative 1, I'm going to get 1 minus 6. Put in negative 1 here, that becomes plus 10 minus 6 plus 9. So I'm going to get 19, 20 minus 12. 1 doesn't work. I'm going to hope negative 3 works. So let's go synthetic. 1, 6, 10, 6, 9, and I'm going to try negative 3. And I get 1, and negative 18, and negative 12, and positive 36. Hold on. I'm probably going to redo this. Let's see. I get 1. I get negative 3 here. Sorry, I was getting ahead of myself. Negative 3 here. I get 3 here. Just 3. Negative 3 times 3, negative 9. And 10 is 1. Negative 3 gives me 3, and negative 3 times 3, negative 9. And sure enough, I've got it. So right now, this thing is factored into x plus 3, x minus negative 3. This would be an x down to third plus 3x squareds plus an x plus 3. And now, when I have 4 terms, maybe I can factor by grouping. Let's give that a try. X plus 3. Out of these two, I can factor out an x squared, and I'm left with an x plus 3. Out of here, if I factored out a 1, I'd be left with an x plus 3 as well. Therefore, I get x plus 3 times, if I factor an x plus 3 out of each of these, another x plus 3, and that leaves me with an x squared plus 1. So as it turns out, this is a double zero. We might take a look at that. If I have this equal to 0, either x equals -3 or -3, it's a double zero, or x squared plus 1 equals 0, which would mean x equals plus or minus square root of 1, and that would be square root of -1 is I, so plus or minus I, giving me factors of x plus 3 squared times x minus I times x plus I. One thing I know about the graph of this thing, let's talk about that just for a moment. It's positive x to the fourth. It's going that way and going that way. It rises to the right, rises to the left. And I know that -3 is a double zero. And it may wiggle around, but it doesn't cross 0 anywhere other than that. So I know this graph comes down, flattens out, and goes up here. Now maybe it wiggles in here, and we could talk about that maybe by looking at sprinters, intermediate runners, distance runners, but I do know that I would have that kind of behavior happening at that -3. At -3, it wants to look like a parabola. Okay, let's take a look at factoring a polynomial. Right, the polynomial is the product of factors that are irreducible over rational numbers. That is like that's our traditional factoring. That's what we're used to doing, rational numbers. We might have fractions in there, but I don't have anything like square roots in there. That would be B, real numbers. So I'm looking for factors of -27, because this is quadratic on x squared, that would add up to be +6. Well, +9 and -3 get the work done. So if I was to factor this thing, which I am to do, I'm going to make my outside product be the bigger of those two things. Could be the smaller as well, but I'm going to go with the +9. I'm going to use the biggest number from here times the biggest number from there, the biggest factor of 1 times the biggest factor of 27 that can get me +9, and that's 1 from here, so I need a single x squared, 1, and I need a 9 here, and that has to be plus. First term times first term equals first term, x squared. Last term times last term equals last term, -3. There's my missing -27. Or there's my -27. Here's my missing -3 right here as well. So I got my +9 and my -3 from my foiling. So that, can I factor x squared -3? Not without introducing, because I need difference of perfect squares, and 3 is not a perfect square, and I definitely cannot factor x squared plus 9 over in traditional methods, so there's A. Now, if I tried if I set x squared plus 9 equal to 0, I'd have x squared equals -9, and I'd have to introduce equals plus or minus 3i. I'd have to introduce complex numbers, and for part B, I don't want complex numbers. Now, this is x squared minus 3 is not, that is not difference of perfect squares, but if I think of this as square root of 3 squared, I can factor this into x plus root 3 times x minus root 3 times x squared plus 9. And these are real numbers. These are not. So part B, as the product of linears and quadratic factors that are irreducible over real numbers. Okay, these are irreducible over reals, and that's quadratic. And finally, in completely factored form, so that's when I get my x is plus or minus 3i. So C is x plus root 3, x minus root 3 times x minus 3i times x plus 3i. Okay, one more here. Use the given 0 to find all the zeros of the function. They're telling me -3 plus I is a 0, but they're not just telling me -3 plus I is a 0. Complex zeros occur in conjugate pairs. So if negative 3 plus I is a 0, so is negative 3 minus I. Therefore, factors I have, x minus this guy would be x plus 3 minus I, and x minus this guy would be x plus 3 plus I. And then I'm just missing one more after that because I need a third one. Okay, I'm going to just superfoil these. The only place I'm going to get x squareds is here. I'm going to get 3x's here and 3x's there for a total of 6x's. I'm going to get a positive x times I there and a negative x times I there, and the conjugate's going to work, those cancel. And I'm done with my x's. Here's where I'm going to get a real number. 3 times 3, that's a plus 9. Then I get 3 i's, but I also get minus 3 i's. And all that's left is the minus I times minus I squared. So that becomes x squared plus 6x plus 9 plus 1, or x squared plus 6x plus 10. And now I could long divide this into here. But I can show you a trick on this. If we trust our work here, we should be able to say there's just one more factor with x in it. And first times first has to equal first. X squared times what is 4x cubed? 4x. Last times last equals last. 10 times what is negative 10? Negative 1. Could we possibly do that, hocus pocus? Let's take a look. Let's superfoil this thing. X squared times 4x is 4x cubed. Where am I getting x squareds? X squared and minus 1, that's minus an x squared. And here's plus 24x squareds. 24x squareds minus an x squared plus 23x squareds. How about plain old x's? Here's minus 6 of them and plus 40 of them. Plus 40 minus 6 plus 34x, and 10 times negative 1 minus 10, and we got it. Pretty slick. You can do that when you're only missing one factor, but it's certainly worth checking. You also could have taken x squared plus 6x plus 10 and long divided that into 4x cubed plus 23x squared plus 34x minus 10, and I'm going to claim we would get that same factor. So let's make certain we've answered this. Use the given 0 to find all the zeros. So here's our zeros. Negative 3 plus or minus I, that's 2 of them. And our last 0 comes from right here, where 4x minus 1 equals 0, or x is 1/4. Sorry, x is 1/4. There's our 3 zeros. And if we needed this thing in completely factored form, I would just put my 4x minus 1 right up here. Okay, thank you for your time and good luck, and we will certainly be spending some time with the practice on these problems.